Hi, welcome to Fun Adventures with the Event Loop. I'm actually just recovering from a bout of COVID, so if I lose my voice halfway through, I'm just going to pick someone randomly from the audience to finish this off, so be ready. Also, I spent ages making this animation on this slide, and I always forget that no one ever sees it because the slide's already up when you start, so I'm just going to refresh the page real quick. Oh. Yeah. All right, so hi, my name is Erin Zimmer. I work for a company called Cash App. You may not have heard of us because the product isn't actually available in Australia, but we do have offices here and we are hiring. And I didn't say it before because I was like, I'll wait till I'm down in front of everyone and you'll remember me more. So we have a product that provides banking services for the underbanked, which is a big issue in the US. Lots of people can't get bank accounts, and even when they can get bank accounts, they can't do stuff like transfer money to their friends instantly. So we do some cool stuff with that. We do lots of machine learning, big data, Bitcoin, share trading, all that kind of stuff. So if you're interested, we particularly like Kotlin developers, but you don't need to learn Kotlin. You don't need to know Kotlin to come work with us. So come chat with me. If you would like to argue with me about this or anything else, you can get me on Twitter at Erin J. Zimmer, and the slides are at eventloop.ez.codes, but I'll be honest, the demos don't work. So good luck. All right, so let's start off with what actually is the event loop. Who here is a front-end developer? Cool. So some of you might actually be interested in this. The event loop is basically how JavaScript how the browser manages running JavaScript code. So if we look inside the browser's got lots of different bits inside of it. It's got a bit that parses and executes JavaScript. It's got a bit that makes network connections. It's got a bit that runs timers. It's got a bit that reads and writes from the disk. It's got a bit that manages user interactions. It's got a bit that parses and renders HTML and CSS, and probably some other bits. So these bits here, these aren't the event loop. These are the web APIs. And this bit here is the JavaScript engine. It's not the event loop, but it's sort of the bit that the event loop is dealing with, I guess. So all different browsers have different JavaScript engines. The one that's probably the most prevalent is V8. This is the engine that runs Chrome and all of the Chromium sort of browsers like Brave and Opera and things like Baidu. There used to be I think it was called Edge.js, but as we know now, Edge is now also running Chromium, and I should probably update my slides. The Safari engine is called Squirrelfish. I don't know if this is the official logo, but it totally should be. And the Firefox engine is called Squirrel Monkey, and I couldn't find a logo for that one either, so here's a picture of a squirrel monkey. All right, so the way that what the event loop does is it sort of allows the web APIs to talk to the JavaScript engine and to execute JavaScript code. And it looks something like this in sort of the most basic form. It's an infinite loop. It's going to keep running forever. Each turn of the loop, it's going to take a task off the task queue, and it's going to execute that task. So that should all be quite clear now, I guess. You all understand what's going on, except maybe a couple of small questions, like what's a task? What's a task queue? How does task get in the task queue? So let's start with what's a task. So basically, any bit of JavaScript is a task. So here we've got some HTML that's got some JavaScript in it. The HTML parser is going to get to this. It's going to go, JavaScript, I don't know how to deal with that. It's going to pass it off to the JavaScript parser, and the JavaScript parser is going to make a task. It's going to put it in the task queue. So it's going to look something like this. It's going to put the task in the task queue, and then we're going to execute the task according to that little bit of code that we had before. So the important thing here is that this is a queue, right? So each task that gets added to the queue is going to be executed to completion before anything else happens, right? Your bit of JavaScript is guaranteed to either run start to finish or until something breaks and it throws an exception. I don't know how you write your JavaScript. And the other important thing here is that the things are going to happen in order, right? The order that they arrive in the queue is the order that they get executed. All right. So why is JavaScript like this? I promise you it's not just doing it to be difficult. So there's sort of two parts to this. The first is that JavaScript running in the browser is single-threaded. And there's a reason for that. The reason is that most of what the JavaScript in the browser is doing is dealing with the DOM, right? The document object model, which is the data structure that represents the page. And this is a great big data structure that deals with everything that's happening on the page. So if we had multi-threaded JavaScript all touching the same data structure, things would get pretty messy. So it's much simpler just to have it single-threaded. Or maybe it's because JavaScript was written by one guy in 10 days and that's all he could manage. Could be either. So browsers, on the other hand, are multi-threaded, right? They can do heaps of stuff at the same time. They can make network requests and read from the disk and respond to user input and run JavaScript all at the same time. So we need a way to get that multi-threaded browser happening to sort of go into a single-threaded JavaScript environment. So if we say wanted to do a set timeout, we can call set timeout. What's going to happen is we're going to say, hey, web APIs, could you wait 3 seconds and then run my callback function? And the web API is going, no worries, JavaScript, you keep doing what you're doing, and I'll take care of this in another thread. And it will look something like this. Our JavaScript is running. It's going to set a timeout. The timer is going to run, and then it's going to get added to the queue, and it's going to run. The important thing here is if our JavaScript is running and we set the timer, we can then also have user interaction and network requests and all of this other stuff sort of going on at once. And we'll just deal with the timer task when it's ready. This is also something that's important in JavaScript. If you are using set timeout or set interval, they're guaranteed to run after the timeout, not on the timeout, because you'll notice if there's a bunch of things in the queue already, when your task gets added to the queue, you've got to wait for all of those things to happen first. Right? So your set timeout with a 3-second delay is going to happen sometime after 3 seconds. OK, so now we understand what's going on in our event loop, right? It's an infinite loop. Each turn of the loop, we're going to grab the first task off the queue, and we're going to execute that task. Are we all OK with that? Yes? Cool, because it turns out it's a little bit more complicated than that. We also have the rendering pipeline. So the rendering pipeline is the bit in the browser that takes all of the HTML, constructs the DOM and the CSS object model, and smooshes them together and makes the actual bits, pixels that get painted on the screen. So the rendering pipeline doesn't run after every task. So the browser's a bit clever, right? You notice how often the monitor refreshes. So instead of running after every task, it's going to wait for the refresh, right? So if you've got a 60 hertz monitor, that's going to happen every 16 milliseconds. So we're running some JavaScript, then we're going to render after 16 milliseconds. So we can have some tasks here. The browser is just going to execute these tasks, and it's just going to keep going until it gets to the 16 milliseconds. Oh, is it going to make it? Oh, 1 minute. And then it will run the rendering pipeline. So the important thing here is if there's a task that's running at the point where the rendering pipeline wants to run, then the rendering pipeline has to wait for that task to finish, right? So if you've got a long-running task, it can cause the rendering pipeline to drop frames. And your website is going to get jittery, and it's not going to be a good user experience. So yeah, make sure that you don't have those sort of long-running tasks. So how can we do that? Imagine we've got this function here, which is just going to take an action, and it's going to repeat it a given number of times. If the actions are fast and the number of repetitions are low, this is fine. It's not going to cause any problems. But if this is running tens of thousands or hundreds of thousands of times, it could easily take more than our 16 milliseconds. And I mean, 16 milliseconds is only on 60 hertz monitor, right? If you've got a 100 hertz monitor, it's going to be 10 milliseconds. So it could take a long time. So what we can do in this situation is we could break this up into multiple tasks. So instead of having a single function that runs one task, we can bust out a bit of recursion and have it so that the function is called recursively, but each time it's called, it's wrapped in a set timeout, which creates a new task. Right? So this will, each action will be its own task. Each repetition of the action will be its own task, and it's not going to block rendering. So this is okay. There is a bit of overhead associated with creating so many tasks, which means that this will actually run slower than the original version, but it won't block rendering. Not everything can be broken up like this, though, and it's not amazing. So sort of the preferred way to handle this situation is to use web workers. So you can create a web worker by calling new worker and passing in a JavaScript file. Then you can communicate with your worker by calling worker.postMessage, and then the code inside the job.js file there will run when it receives a message. So web workers, remember before when I said the JavaScript in the browser is single-threaded? That was a lie. JavaScript in the browser is totally multi-threaded, and web workers are essentially the thread mechanism. The limitation of them, though, is that they don't have access to the DOM, right? So they're solving that problem of the multiple data access to the same data structure, multiple threads accessing the same data structure. Web workers are available in all of the browsers, including IE, so definitely check those out if you do have some kind of long-running tasks that don't need access to the DOM. Okay, so now our event loop looks like this. It's an infinite loop. Each turn of the loop, we're going to grab a task off the queue. We're going to execute that task, and then if it's time to repaint, we'll repaint. Are we all good with that? Yeah, cool. Because it turns out it's a little bit more complicated than this. So an event loop has one or more task queues. This is straight out of the relevant spec, because I had a lot of spare time during lockdown, and reading specs was fun. So what I thought was, I'll jump in, I'll get some browser code. Like, browsers are all open source, right? I'll look in and I'll find one that has this sort of multiple task queues, and I'll show you a really good example of how task queues work. Except browsers are written in C++, and I'm a JavaScript developer. And as far as I can tell, C++ is mostly just punctuation and the word delegate. And I don't know what's going on there, so I'm not grabbing a real-world example. Instead, we're going to use the example that's in the spec. So it is made up, but at least it wasn't me that made it up. Okay, so here we have an event loop which prioritizes user input. So you can see if we have some JavaScript running, it goes in one queue. If we have user input, it goes in the other queue. And timers and network requests go in the first queue. And this particular event loop is always going to run the tasks that are in the user input queue, right? As long as there's anything in the user input queue, it will run that. And once that's empty, then it will run the other tasks. Yeah, so that's basically browsers can do whatever they want with that. There are a couple of rules. So the queues can be executed in any order. So that particular one, we said we're always going to execute the user input queue. We could have said we're going to pick 2 off the first queue, 1 off the second queue, 3 off the first queue, whatever we like. Tasks are executed in the same order they arrive. Queues are still queues, right? And tasks from the same source must go in the same queue. So all of our user events go into the user event queue. All of our timer events go into the same queue. This is not super relevant for browsers. As far as I know, most browsers actually just use a single queue, but Node uses multiple queues like this. And the way that it handles events versus timer callbacks and things like that means that it's affected by how it structures its queues. But we're not talking about Node today. Okay, so this is what our event loop looks like now. It's an infinite loop. Each turn of the loop, we're going to pick a queue. Then we're going to take a task off the queue. Then we're going to execute the task. Then if it's time to repaint, we're going to repaint. Is that all good? Yeah? Cool. Because it turns out it's a little bit more complicated than that. We also have something called microtasks. Now, microtasks are tasks that happen between a task and rendering, right? So they're sort of like a higher priority task that are going to happen between the normal task queue and when the rendering pipeline runs. They were invented for Mutation Observer. So Mutation Observer is an API that allows you to watch a DOM element, and when anything changes in that DOM element, a callback is going to get called. And the thinking was that if you're watching a DOM element change and you're reacting to it, you probably want to make some other change to the DOM that you want to happen before the rendering pipeline runs. So microtasks allow you to do that. The use of microtasks that's much more popular these days that you might be more familiar with is promises. So every time a promise is resolved, it's a microtask. You can also just make microtasks. There's a window.q microtask API. Probably don't, though. This one is more intended for people who are building frameworks and libraries like React or Angular or things like that, where they're doing their own virtual DOM and they want to be able to handle things and manage where they fit in the rendering cycle and stuff. But promises, you can use promises. They're great. Okay, so what this looks like is if we have a task and say it generates a promise goes in the microtask queue. Maybe it makes lots of promises. And they're all going to run, right? And we're going to keep running the microtask queue. As long as there are tasks in the microtask queue, we're going to keep running the microtask queue. Even if the rendering pipeline wants to run, we're going to keep running the microtask queue. So it's absolutely possible to block rendering with microtasks, even if they're quite short. So an example of that, we have here a bit of code that is we're going to click the button, and it's going to start generating tasks. And it's going to show us how many tasks it's generated. It's going to be pretty boring, to be honest. We click the button, and it shows us how many tasks. Lots and lots of tasks are being generated. That's all fine. We can click stop because we're bored of it. Move on with our lives. But if we do the same thing with microtasks, so this is just creating a microtask, which creates a microtask, which creates a microtask. If we click the button, oh no, it's in a different tab and you can't see it. Oh, share this tab instead. Go. There it is. So if you click the button, it just breaks, basically. I can't interact with anything on the page. What you can't see up there is that it's actually crashed and Chrome is like, hey, this is unresponsive. So let's not do that anymore. And let's go back over here. Oh no. Oh no, we've stopped sharing completely. I didn't consider this. Okay.
We have the technology.
Yes. After 2.5 years of doing all of my social interaction via Google Meet, I am totally nailing it. Okay, so what happened with that example, apart from some sharing failures, is we run our initial task. Actually, we click the button, and that generated a promise, which generated a microtask, which generated a microtask, which generated a microtask, and that just sort of kept going, right? So there was no way for the rendering pipeline to run, and there's also no way if we have more user interactions or anything, there's no way for anything else to happen. We're just doing microtasks. So don't make infinite loops of microtasks is the takeaway from that one. Okay, so now we have our event loop. Looks like this. It's getting a little bit more complicated. So it's still an infinite loop. Each turn of the loop, we're going to pick a queue. We're going to take the first task off the queue. We're going to execute that task. And then as long as there are tasks in the microtask queue, we're going to execute all of those tasks. Then once that's done, if it's time to repaint, then we'll run the rendering pipeline. Cool? We're all still good with this? Yeah, cool. Because it turns out it's a little bit more complicated than this. We also have the animation frame callback queue, which is a mouthful. So we can add tasks to the animation frame callback queue by calling request animation frame and passing in a callback. So why might we want to do that? Imagine that we wanted to do this really fancy animation, which makes a square move across the screen in sort of a sine wave pattern. Now, I can guarantee everyone who's ever had to do anything like this, the first thing that you do, and I say you, I mean me, is write something like this, right? We say we've got a loop that's going to keep running as long as the box hasn't reached the right-hand side of the screen. We're going to figure out how much time has passed, and then we're going to calculate where the left and top position of the box should be at each time, which all seems very reasonable, except when you actually run that, what you get is this, right? The box just appears at its final position. Because that function is a single task, so the whole thing runs, and we never render in between, so the square is you never see it in any of its other positions. So we know from before that how we can solve this. We can break it up into multiple tasks using set timeout. So just like before, we've done a bit of recursion here, which means that now every time this loop runs, it's running in a new task. Which means that it's going to run the task, run the task, run the task, run the task. Oh, I started to think 16 seconds was a bit long. Run the task. And then it's going to render. right? So we're going to see the box move across the screen. We can do that, but as you just saw there, we end up performing a lot of tasks that we don't really use, right? We calculate position, but then we don't render. So we just kind of throw that calculation away. Then we do another calculation, throw it away. Then we do another one, throw it away. Then we do one and render. So we can, if you can imagine, like the green tasks are the ones where the rendering pipeline ran. That's a lot of wasted work. So what we can do instead is create an animation task using request animation frame, which is basically exactly the same, except we call request animation frame instead of set timeout. So the way that that one works is that we have our initial task run, and it creates an animation task. And the animation task doesn't run, right? It just sits there and it waits. And some other JavaScript could be executed in the meantime. Maybe some other stuff is happening. And the animation task is just going to sit there and wait until it's time to render, and then the animation task will run, and then the rendering pipeline will run. Which means that we can have an animation task sitting there waiting, and when it gets time, when it runs, it can then create another animation task, which will then sit there and wait. The important difference between the microtasks and the animation tasks, apart from the fact that the animation tasks only run immediately before the pipeline, is if we have a bunch of animation tasks in here, when the rendering pipeline runs, they'll all run. But if we add any new tasks during this sort of render, the new tasks won't run, which means that we can use this as a way to set up animations, right? We can write this frame, and then we can call and set up request animation frame to set up the next frame, hence, I guess, the name. Yeah, so it gives us a good way to animate things. So here we have our squares animating again. The top green one is request animation frame, and the bottom pink one is using set timeout. You see, for this particular example, there's not much difference. There's not a lot going on in the screen there, so the wasted processing for the set timeout doesn't make that much difference. But this is the number of tasks that were completed for each one. So the request animation frame ran 690 tasks, and the set timeout one ran 2,621 tasks, so about 4 times as many. That's good enough maths, yeah. So yeah, you can imagine that if your page has a lot going on, or even a normal amount going on in today's web, then wasting all of these tasks is going to have huge impacts on your performance. Request animation frame is absolutely available in all of the browsers, except for Opera Mini, but honestly, Opera Mini doesn't support animations, so it's probably not a problem. All right. Yeah, so request animation frame is also good if you have anything that needs to be batched up before just any sort of DOM stuff, right? It doesn't have to be an animation. This is actually how framework writers dealt with not having, being able to create microtasks, is that everything that React is about to render waits until a request animation frame and renders it just before the, runs it just before the render happens. So anything that you want to batch stuff up and only have it run just before render, request animation frame is good for. Okay, so this is what our event loop looks like now. It's an infinite loop. Each turn of the loop, we're going to pick a queue. Then we're going to take the first task off the queue, and we're going to run that task. Then, as long as there are things in the microtask queue, we're going to run all of the microtasks. Then, if it's time to repaint, we're going to run the tasks that are currently in the animation task queue, animate that queue, and then we're going to do the repaint. Okay, are we all cool with this? Yeah, cool, because it turns out that's it. That's the whole thing. That's the event. I mean, we could go into Node where it gets a bit more complicated, but I think this will do for tonight. Okay, so things to remember. Most importantly, don't block rendering, break things up into smaller tasks, offload things into service workers, web workers if you need to. Promises are going to be microtasks, which means that they can potentially block rendering in ways that other tasks don't have the ability to. Anything that you need to animate or batch, do it with request animation frame. Also, hopefully this helps explain if you've ever written a bit of code where you're like, I'll just wrap it in set timeout, and then it works. This is probably why. It's something to do with tasks. And for all the React developers out here, I'm sure if you've ever written a test in React, at some point you've seen this warning. I'm not going to go into what actually happens with it at the moment, but if you ever are trying to understand what's going on there, try thinking about it in terms of tasks and how things are broken up and how your test is a task and anything asynchronous is a different task and the order that they might be running in. Yeah, so that was all that I had. Thank you. Are there any questions? Yes.
The question animation frame seems like a very wonky way to implement a game loop. Basically, a game loop is like handle user input, handle logic, and then render.
Yes.
And it's like, when I think about stuff in the browser, that basically these days, even apps are very heavy in animation. It seems like they would always want to have a render animation frame before every rendering. And having to request it every time and keep the state, but that request I don't want to put two in because then I'll do the thing twice. And it seems like all you want is just to register, just call me before every frame. And do it once and always have a render loop, rather than this weird request animation frame. Which I'm sure there was a reason you have to redo it every time. It's some kind of historical mechanism that they thought would be more efficient, or I don't know what.
So a wonky game loop is basically a really good description of the browser. It is 100% an input device that should be working like that, and it doesn't. These things are all just stuff that's sort of, I mean, initially the web was, displaying documents, right? This animations and everything are kind of all just tacked on, and everything has to be tacked on in a way that is backwards compatible with everything that's come before, like the first website that was ever written still displays in modern browsers kind of thing, right? So the answer is history, where we've started off with the wrong model and we're trying to hack it together to where we're at today, and that's why the web is janky.
There must be frameworks that just abstract it away and like allow you to write things as if it was not janky.
Yeah, absolutely. There's all kinds of animation frameworks. Also, if you're doing real animations on the web, you're going to use a library. You might be using Canvas rather than writing things in the DOM. Because that's the other thing too, right? The rendering pipeline is optimized for rendering things in the DOM. So there's a whole bunch of stuff that is happening there automatically that you don't have to worry about. But if you're like making a game or something, you're not going to be probably doing it in the DOM. It's not what was intended for. Yeah.
Is that me?
That is you right there.
Sort of that's a good point. Like I was going to say, you should probably focus on making sure your website's accessible and doing all of those basic things that aren't as fun as animations well before thinking about animations. But also, it's really a performance problem, isn't it? And are there any tools that go-to tools for finding out bottlenecks and in the browsers themselves, like if you look in Chrome, or I'm not sure what the performance tools are like in Firefox, but you can look in Chrome and you can see like where it's painting, what's taking the time, where the JavaScript's running, what's using the memory. Like the browser themselves just have these really good built-in tools for doing all of this analysis. Totally recommend having a look in there if that's a problem. I mean, it's almost certainly a problem. Yeah, Mike.
Where does WASM WebAssembly sit? Is it completely outside of anything DOM, or was it?
I believe it's outside of the DOM. I think it works sort of like a web worker kind of situation, but I'm not sure. WASM is one of those things that I'm sure is an excellent idea, but I've never had a use for.
It is sandbox, and it's got a specific interface for crossing that boundary.
Yeah, there you go.
So, coming to a point, so does that mean it is subjected to how much RAM available is there in the device? Like in terms of how the device is being loaded and all that, based on the same code? Like how much subjected is it to the resources available in the system?
I mean, obviously it's subject to the resources that are available, but the browser, it creates a separate sandbox environment for each tab. So each tab gets its own resources. It is pretty limited, but I don't know the intricacies of how it's actually allocated. Sorry.
I'm going to throw in one more question.
Yeah.
Any chance that you are related to Hans Zimmer?
There's always a chance. Hi.
It's been a while since I've been a JavaScript developer, but I thought the purpose of promises was to avoid blocking the event loop, or is it the nesting of promises?
Yeah, the example that I showed there is pretty contrived.
Right.
Probably not going to happen.
Yeah.
But yeah, so they generally they're like anything else, right? If you make them long running, they're going to block.
Right.
But yeah, there's just, I guess there's that little bit of danger there, and that if you have multiple of them, they are going to block in a way that multiple tasks wouldn't.
Right.
And if you don't chain them, they can come quite long.
Do web workers have to be in their own file?
I think so. Yeah, but I'm not sure.
Seems weird.
Um,
Every time I want to use one, it's like you have to make your own file, and
yeah,
it's always so awkward outside.
yeah, as far as I know, the API is that you pass in a file name, but yeah, I don't know, sorry. But maybe there's someone from Google. Yeah, up the back there.
Not for the fundamental presentation, but did you actually make that on your own set of like presentation stuff?
It's using a framework called Reveal.js. Yeah. All right, we can go to the pub.